Okay, so the topics for today, which we are going to cover, are basically. So yesterday I've discussed about the graph representations, the two ways to represent graph. Today I'll be covering about. So yesterday I also discussed about what min heap is and how you can sort of represent that in the format of a binary tree as well and an array as well. And I also talked about what a max heap is. It's nothing but a little different from min heap, but the operations are converted from less than to greater than, right? In the coding part itself. Okay. So today we are going to cover the operations of min heap, the operations of min heap. And once I cover the operations of min heap, I'll switch to the coding part and explain how you can uh, write that. Also, I don't need to explain about the operations of max heap because all of them will be same and interrelated. And as I mentioned, less than equal to will be greater than equal to correspondingly. Okay, let's see. So the few operations of min heap which we are going to discuss today are as follows. So there's peak, then we have sift up, then we have sift down, then we have build heap. Build heap. Okay. And also there are a few other operations like insert and remove. So you might be wondering that, okay, so there are a lot of operations here, a lot of things going on. So I'm going to explain which operations are independent on which one. Okay, so basically peak is an independent one. It does not depend on any other functions here or operations. Build heap depends on sift down. Okay, build heap depends on sift down. So build heap is dependent on sift down because when I'm calling build heap, actually sift down is also being called just to readjust the elements in the array. Okay, when I'm calling insert, then sift up is being called. So I can say that insert is dependent on sift up. When I'm calling remove, then remove is dependent on sift down because when I'm calling remove, sift down has been implemented in itself, in the function itself. So when the function defined remove is there, then in that case, sift down, so SD is also being called. So I hope you get my point, right? So they are interrelated. So I'll just wait for a couple of minutes and then I'll just start with the operations. Okay, so just going to wait for a couple of minutes. Looks like I forgot to share the screen. So these are some of the topics which we are going to cover. So these are the few operations of min heap: peek, sift up, sift down, build heap, and insert and remove. Okay, let's begin. So I hope you are aware of what a min heap is. So I'm just going to draw a random tree here. Like I forgot to share the screen. So 7, 11, 23. 11 is going to have child like 17 and maybe 31. 23 is 30, 49. And for 17, I can have 101, then maybe 18. Okay, so this tree which I've drawn is a complete binary tree and a min heap as well, because I can see here that for each and every node, its children are greater than the node, right? So what I'm talking about is that, okay, so the min heap property says that the root value is the smallest value, which I can see it's true here, right? But I also have to check that, okay, so for each and every root, so if I just consider 11 as the root, then all of the values up here are smaller than the root value, right? So 7 is smaller than 11 and 23. Okay, pick any one. 23 is smaller than 30 and 49. 11 is smaller than 17 and 31. And if I pick 17, 17 is smaller than 101 and 18. So I can happily say that this is a min heap, okay, and also a complete binary tree, which we have discussed in the yesterday's session. Let's see. So the first operation says that, okay, so basically the first operation says that peek, okay? The first operation says that peek. What do I mean by peek on a general basis? Just forget about programming. So when I talk about peek, it means that, okay, so I'm just going to take a peek at something, right? So when I'm talking about this tree here, I just want to peek what? The smallest element, right? I don't have to do anything with the largest element. If I had to do anything with the largest element, I would have switched to max heap instead of min heap. So as of now, I want the smallest element. So I can just happily take a peek at this. So the peek functionality, what it does is, it says this, that, okay, so return the root value, or the value at the 0th index, which means the first index itself, right? The first most block in the array, or return the root value or the value at the 0th index, or the minimum value of the array, or min heap, because that's what we are looking forward to, right? So peek's functionality is this itself. I hope you remember one data structure which I've mentioned, which I've taught earlier as well. I believe so. It's stack, right? It's stack. In that also, in stack we also have push and pop operations, right? But in stack also, if I just want to take a look at the topmost element, so if this is the stack and I want to take a look at this topmost element, then I can also implement a function like peek here, because that's also going to give me the topmost element of the stack. Okay, so it's not like peek is restricted to min heap only. It can be implemented with any other data structure as well. Okay, so the peek functionality is that, okay, so return me the minimum value of the array or the min heap. Okay, great. So peek function has been done. Let's see what we are left with. So we are left with something called removal. Okay, we are left with something called removal. So let's see. Maybe instead of remove, I can just explain what an insert operation is. Insert operation in peek. Well, you might be like, okay, so when I have an array of integers represented in the form of a heap, right, or the min heap, then I can just insert an element here, right? So maybe I can just draw the array. So the array elements are going to be as simple as this. So 7, 11. Okay, I think I'll fall short of space here. Yep. So 7, 11, 23, 17, 31. Then we have 30, 49, 101, and then 18. Okay. So I'm just going to draw a few blocks here, couple of them. Yes. So I'm just going to draw a couple of blocks here. Great. So this is basically the min heap. If this is the tree here, then I can represent that in the format of an array. And this is something I've discussed yesterday. Okay. So you might be like, okay, so I'm talking about an insert operation. So I can just happily insert one value. Suppose I want to insert a value called 6, right? Not called 6, but a value numbered 5. Suppose 5. Okay, I want to insert a value 5. Then you might be like, okay, this is quite easy. So what I'll do is I'll just insert the value 5 at the very end. but it's not simple as that. You have to rebalance the array here. Okay, you have to rebalance the array here, and you will be like, okay, why am I rebalancing it? Right? Why am I rebalancing it? You have to rebalance so as to maintain the property of min heap. Okay, so it's not easy that, okay, I can just put in the value 5 here and then I'll be good to go. We'll see what the process looks like. So when I'm talking about an insertion operation, insert 5, what I'll do is, this is what the algorithm says. Okay, I'll just write these small steps here. So maybe I can just talk about the first step. I'll insert, or maybe I'll append the new value. I'll append the new value. Okay, I'll append the new value at the end of the array, at the end of the array, which is representing my min heap. Okay, it's not a regular array, right? It's a min heap array. So append the new value at the end of the array. Okay, this is my first step. Let's see what we can do further. What I'll do is, for the current index, or for the suppose, let me explain it in this way. Suppose when I am inserting the new value at the end of the array, the index it is stored at is idx. So my idx is nothing but the index where my new value is stored at. Okay, stored at. So idx is nothing but the index where my new value is stored at. Now what I'll do is, third step maybe, so compute the parent index. Okay, compute the parent index, parent idx of the current idx, which is nothing but this index, right? So current idx. Once I've computed the parent index of the current index, right? Sounds a little bit rough here, but it's okay. What I can do is I'll compare that. Okay, so I'll just compare that the value. Okay, that does not make sense. So compare if the value, or compare the values will be great, right? So compare the values of heap value, right? So of number at the parent index, okay, number at the parent index and the current index, And now at the fifth step, I can happily write that, okay, so if the number at the parent index, so num at parent index PIDX is actually greater than, okay, it's greater than the number at the current index, In that case, I'll swap. So I'll just highlight this. In that case, I'll swap. That's it. Well, this might be looking more like a complicated operation, but it is not. It's quite easy. The lines of code is basically 4 or 3 to 4 lines of code, nothing much. So what did I talk about? That, okay, append the new value at the end of the array. Then I'll just compute the parent index where the current index, where the value is stored at as of now of that parent. So I'll just compute the parent index. Okay. Now, when I have the parent index, I'll compare the values at the parent index and the current index. So if suppose this is the parent index, this is the current index. If this number, the parent one, right, is greater than this one, then I'll just swap, right? Because I'll gradually have to bring the smaller number to the top, and hence the property min heap. Okay. So let's try to implement it here itself. So I'm talking about an insertion operation and a number 5. Let's see what we can do. I'll just use a white color to make it more clearer. So where should I insert 5? Well, 5 will come up here. It's going to be the left child of 31. Okay, it's going to be the left child of 31. Now that this has been done, notice how I am going to compute this. Okay, so for 5, what is the parent index? Well, I can compute it with the formula, but as of now, diagrammatically, by the look of it, can I say that the parent of 5 is 31? Yes, I can say that. Okay, now I'll compare the values. Okay, is 5 less than 31? Yes, it is. So I'll just swap. 5 and 31 here. So 5 comes up here, 31 is right here. Okay, great. Now, should I stop here? No, I'll have to continue this until and unless my condition that the parent index is greater than the sort of like the child index satisfies, right? So suppose I reach a point, something like this. So suppose I reach a point 40 and then 55, right? Suppose this is the representation here. Suppose this is the representation here. So I'm considering suppose 55 and 40. So at this point of a time, I can break or I can stop my while loop here, right? While loop, for loop, whatever the loop is, right? That's it. So let's see what we can do now. So as of now, should I stop? No. Let's see why. So as of now, I'll be keep track of the element or the index at where the 5 is, right? So again, I'll compute where the parent is, right? So 5's parent is 11. Is 11 greater than 5? Or more formally, is 5 less than 11? Yes, I'll just swap. So 5 gets swapped with 11. Right here, 5 comes up and 11 comes up. Should I stop now? Let's see. Let's see if I have to stop. What is the parent of 5 as of now? Well, it's 7, right? So is 7 or is 5 less than 7? Yes, I'll just swap. So as of now, I can happily say that this tree has been rebalanced. Okay, this tree has been rebalanced. Now you might be like, okay, what is the path which has been rebalanced currently? So this is the path which I'm talking about. This is the path which we have rebalanced. Okay, this is the path we have rebalanced. If you notice properly, then I might give you sort of like a task on your own. So you have to compute the time complexity of this. Okay, so I'm just going to give you the hint that time complexity will be basically big O of log n. Not really a hint, the answer is there, but you have to know that why is it log n, okay, and not a big O of n log n or big O of n square or big O of n. Okay, a time complexity up here will be big O of log n. Okay, so this is all about the insert operation, right? Quite simple, right? Just pick a number, maybe like which I've inserted here, compare its parent. If it's smaller, swap, and then we can see that okay, so I did not swap this. I guess 5 and 7 will be there, right? So 5 comes up here and 7 will be here. Okay, so this was all about it, right? Our insertion operation has been done. Okay, let's talk a little about the delete operation. Okay, the delete operation. By the way, you might be wondering that, okay, insertion operation has been performed, but I mentioned that, okay, so insert operation is dependent on shift up operation, right? So where is the shift up operation? This process of like swapping, right? So process of swapping and moving the numbers upwards, right? So moving the numbers, moving the new value, by the way, moving the new value upwards, right? Because I can see here that, okay, so 5 was added up here at the very end, but gradually it ended up somewhere on the top, right? Not necessarily on the root value. As of now, it's on the root value. It might be that in some cases, the value was up till here itself, right? So the process of swapping and moving the new value upwards is nothing but the shift up operation. This is it. Okay, this is the shift up operation. Okay, now that this has been done, let's talk a little about the shift down operation. Okay, so I'll just draw the thing again. So 7, 11, 23, then we can have 17, 31, 30, 49, and we have 101, and I guess 19, 18, whatever the thing may be. So this is the min heap again, which I've drawn. Let's talk a little about the shift down operation. Okay, so shift down operation won't really be executed on its own, as I've mentioned, right? So when I'm talking about a shift down operation, it's called when I call the operation remove. Okay, so when I call remove, shift down automatically gets called. Okay, so instead of talking about shift down, let's talk about remove. So when I'm talking about an operation called remove for a min heap remove operation, then I'm essentially not talking about the removal of any random element. Okay, I'm not talking about the removal of any random element. You might be like, okay, you have to remove some element. Okay, so why not remove 31? Why not remove 23? Why not remove 11? So it's not random. So when I'm talking about min heap, I actually want to remove the topmost element or the root element or the minimum value out of all of them. So I'll just have to remove the topmost element. But is it quite simple? Is it simple? No. Let's see how we can make it simpler. So the remove operations says that, okay, so remove the minimum value, value or the root value. Both means the same in this case, or the root value. Let me just check if there is any. No, we don't have any doubts. Okay. So remove the minimum value or the root value. Okay. So is it simple? Yes, it is. Let's see why. So you might be like, okay, so in the array, I can just happily remove what? 7 and I'm good to go, right? I'm good to go. But again, you have to take care of the root value, right? And then you have to compare and then proceed, right? It can be done manually, but to code it out, it might be a little bit complex, which I have not yet tried out. So I'll maybe try out later on. So suppose 7 is here. The best way to do this is suppose the elements, the tree representation had one more element. Suppose it was 45. Okay, suppose it was 45 up here. Now I have to swap the values, right? By the way, this is 18 if you don't get confused. Great. Now to perform the remove operation, the first step in the algorithm, so I'll just mention the steps here. The first step says that, okay, swap the root value, and the very last index, value. Or I don't think so. This will really make sense. So swap the root value and the value at the end. Which means that, okay, so I'm talking about the value at the last index. So it's quite simpler, right? So if this is the array, I'll have to swap this value, which is at the 0th location, and this value at the n-1th location. So I'll just have to swap that. Okay, I hope that makes sense. So this is what the first step in the algorithm says. Okay, let's see what the second step says. After I've swapped that, what I'll do is notice that now my root value is at the last index. It's at the last index because I've swapped that, right? What I can do is in the third step, why I'm mentioning various steps here, so as for clear understanding, right? So now my root value is at the last index. Now what I can do is I can remove, or in programming terminologies, it's pop, right? I can just remove or pop. What I'll pop? The last value, which is nothing but my root value. So this is how I can remove the root value. Okay. Now you might be like, okay, this is very much done here, right? So I'll just swap here 7 and, okay, my bad. So I'll just swap 7 and 45, right? 7 and 45 will be swapped. So 7 comes at the very end. This is my root value, and 45 comes up here. Okay. Now, according to my third step, well, it's saying that remove or pop the last value or the root value. Well, since it's mentioned, what I'll do is I'll just do that, right? So 7 has been removed. You might be like, okay, so this is done, right? I'm happy with the algorithm, but this is not it. Now, what I'll have to do is that from the first index or from the 0th index, right? From the 0th index, perform the operation, which operation? Shift down operation. Okay, shift down operation. And we'll take a look at what shift down operation is. Okay, so now it said that, okay, so I have to perform shift down operation from where? That's the question. So I have to perform shift down operation. Okay, shift down operation, something like this. So I'm gonna swap the elements and I'll just go down, right? Go level by level down. In shift up, I was going up, right? So I'll just start shift down operation from not a random index or not a random value. I'll just start it from the root value itself. That's why I've mentioned here that from the 0th index, which is nothing but the root value, perform the operation shift down. Okay, let's see. Now to understand this, let's understand what a shift down operation is and a little bit about its algorithms. Shift down. Okay, shift down. Let's see. So shift down says that suppose I'm at a current index. Okay, suppose I'm at a, I'll just break down the step quite easily. Okay, so suppose I'm at the current index. Suppose I am at an index I, right? Suppose I am at an index I. Suppose I'm at an index I. I think that won't really make sense. Suppose I'm at an index IDX. Okay. Suppose I'm at an index IDX. Now, what I'll do is I'll get the minimum. I'll get the minimum. Notice what I'm saying here. So I'll get the minimum value of the children of which index? Of which index? So I'm just going to write which index. I'll get it. I'm going to get it for the index IDX because that's where I am at, right? Suppose I'm at an index IDX. I'll get the minimum value of the children of which index? IDX index. Okay. Now that this has been done, now I'll compare. Okay. I'll just compare what? The minimum value, the minimum child value. So suppose minimum child value and the value at the index. Which index? This current index where I am at. So IDX. Okay. The index IDX. Let me just not highlight it properly. IDX. Okay. So compare the minimum child value and the value at the index IDX. Let's see what we can do. After I've compared this, what I'll do is that, okay, so in the comparison process, what I'm checking forward to is that, okay, so if the minimum child value is less than the value at index IDX, in that case, I'll just swap. This is it. And this process will continue until step 4 turns out to be failure, right? So in the step 4, basically minimum child value will be greater than value at index I, right? So step 4 is not validated, something like that, right? So I'll just continue until the step 4 is not validated. That's it. So if the minimum child value, so again, I'm just recall, suppose I'm at an index IDX. Okay, this is an index, right? So maybe I can just explain it in this way. Suppose I'm at an index IDX. This is the child 1 C1. This is the child 2 C2. For the current index IDX, I'll compute the minimum of C1 comma C2, right? And suppose I get minimum, suppose C1. Then suppose C1 is less than the value at the index I. In that case, I'll just swap here. So my IDX will come up here and C1 will come up here. And again, for this IDX, I'll compare for another C1 and C2. And then this process will go on. Okay. Yes. So let's get started with this. Shift down. Okay. As of now, I'm at 45. Let's see what we can do. As of now, I'm at 45. We just write it properly. As of now, I'm at 45. Shift down operation. For 45, I'll consider the children of it, right? So 11 and 23. What is the minimum of 11 and 23? I know for a fact, okay, so 11 is minimum. So now I have the minimum value, which is 11. In this case, 11. I'll compare that. If this minimum value, 11, is smaller than the value at the current index, right? 45. Then I'll swap. Well, I can see here that 11 is smaller than 45. So I'll just swap. 45 comes up here and 11 comes up here. Cool. Now what to do? That's the real question. Should I continue further? Yes, we should. Let's see. So as of now, I'll consider 45. Again, I'll consider its children. So I can see that, okay, 17 and 31 are two possible children of 45. Okay. Now I'll have to compute the minimum of 17 and 31. What is the minimum of 17 and 31? I can say that it's 17. Again, now I have the minimum. I'll compare the minimum with the value at the current index, which is 45. Is minimum 75 less than 45? Well, I can say yes, it is. So, okay. Yes. So I can happily swap 17 and 45. So 17 will come up and 45 will be right here. Okay. Should I continue? Let's see. We'll figure it out. So for 45, again, I'll consider its children, right? 101 and 80. 101 and 18. Okay. Again, consider the minimum value of 101 and 80. So what is the minimum value out of those two? 18. Okay, so minimum value is 18. Now, is 18 the minimum value less than the parent value, which is the 45? Yes, it is. So what I can do is I'll just swap it, right? So I'll just swap it. Let me just quickly undo that. Great. So 18 will come up and 45 will be going down. So 45 comes up here and 18 comes up here. And this is the entire shift down operation. Shift down operation. Well, you might want to verify here, right, that we have done good or not. So let's verify. Is 11 the smallest value out of the entire set of values? Yes, it is. So this many property has been satisfied. Well, let's check for each and every value. So 11 is smaller than 17, 23, great. 17 is smaller than 18 and 31, cool. 23 is smaller than 30, 49, great. 18 is smaller than 101 and 45, great. So this is what internally when we call the shift down operation, this is what's happening. Okay, this is what we are going to implement in the coding part as well. So it's quite simple, as I mentioned in the steps here, which I've mentioned, right? For any index, I'll consider its children value, and for the children value, I'll have to compute the minimum. If the minimum is smaller than the parent value, I'll swap, else I'll break out of the while loop or the for loop, whatever it is. Now, here is an edge case to handle. Okay, here is an edge case to handle. Let's see what that edge case is. So the edge case is that, suppose for an index, I'm computing the child one index and the child 2 index. So C1 and C2 index. Okay, C1 and C2 index. But suppose I'm at this current index and it has only one child. It has only one child. In that case, if I compute the C2 index, it will happily turn out to be a number, right? So the C2 index will be computed as IDX into 2 plus 2. Now this is my C2 value, right? So I have to also check that is C2 exist? Does C2 exist? And how will I check that? Just check with a very small condition that if my C2, just forget about if also, just the small condition will be as simple as this. So is C2 less than equal to my end index, my end index. And what is my end index? End index is nothing but the length of the heap minus 1. So this is something like n minus 1, right? So that's how I'm going to check for it. Okay. So this is a case which I'm talking about when there is only a child here when there is only a one child, and that is also a left child, right? Because it's also following the property of complete binary tree. It's going to be filled from as left as possible to the right. Okay. So after computing C2 for each and every index, I have to also check that, okay, so is the C2 in range? Is the C2 is actually in the heap? Then I'll proceed for the minimum part. Else I know for a fact that, okay, so if there is only one value here, then that is the minimum, right? So suppose I'm talking about two numbers here, 7 and 11. What is the minimum of them? Okay, I can say 7. But when I'm talking about a number 55, only a number 55, then what is the minimum? Well, it has nothing to compare it with. So I can just say that the minimum is 55. But when I have two numbers, I'll have to compare it. That's it. So this is a very small case which you have to handle, and we can handle that very easily. So we have discussed how many operations? We have discussed peek, we have discussed insert and remove. And therefore, after discussing insert, we have discussed about shift up operation. And with the discussion of remove, I have discussed about shift down operation. You might be like, okay, so I'm left with build heap operation, right? Build heap operation. Let's talk about it. Build heap. I'll just check if there is any questions. Okay, there's no question as of now. Let's proceed. So build heap, right? Let me just take a very small array here. Suppose I'm just going to take a array at random, maybe of length 8. Okay, maybe of length 8, so that it's easier for you guys to understand. Okay, 1, 2, 3, 4, 5, 6. So I'll just write the indices here: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Now suppose you're given an interview. Okay, you are giving an interview, and the interviewer gives you an array of numbers. In this case, the array length I can see is 10, not 9. Okay, it's 10. And I'm just going to fill up with random values, like it can be as random as possible. So suppose 100, 5, maybe 45, 3, 6, 7, and then I can have value like 3 once again. So maybe not, I'll just not repeat the values here. It can be repeated. It's not like it's not repeated. So as of now, I'm not repeating it. I'll just also mention how to handle if their values are repeated. So 6, 7, 8, I can have 9, 13, and maybe 41. Okay, great. I've just written some random values in an array of length 10. Okay. And now in the interviewer gives you this array and asks you to implement a function which will convert this array into a min heap or a max heap, whatever the case may be. So suppose let's talk about the min heap first. Okay. So what is going to happen? What is going to happen? Suppose you will be like, okay, so this array is there, this array is given, the length of the array n is given, and you have to implement a function which will convert it into a min heap. So then you will recall that, okay, so there is this function called build heap, right? Build heap, which I'll implement. I'll explain in a second. But this build heap is also going to make use of the shift down operation. And therefore, I have explained shift down operation earlier today itself, right? So that's why I explained shift down earlier. And instead of jumping to build heap first, I'll explain shift down and shift up and peek and insert and remove operations, whatever the thing is, right? So let's get started with this. So my very small, I'm just going to write a very small algorithm here, which you might follow here, okay, which you can follow. Let's see what it says. It says that the first step, okay, the very first step, let's see what it says. That consider the latest parent. I'll explain what the latest parent is. The latest parent, or you can even compute, or you can even think this of as, instead of latest, you can even think this of as recent parent. Consider the latest or the recent parent. Okay, I think I've written the parent twice. Just get rid of that. Great. So consider the recent parent and move. Suppose I get the index of it, right? So suppose I'm going to get the index of the recent parent. So suppose the recent parent, why am I talking about recent again and again? I'll explain that. Because if I just talk about a parent, I'm talking about any parent, right? In the tree or the array. So suppose the recent parent is at index, which index? Suppose idx is at index idx. Okay. Now the third step, what does it say? Let's see. The third step says that the parent is at index idx. Loop, okay, loop in the array, definitely in the array. From where? From the index idx, from idx till 0, which means that as soon as you find the index at which the recent parent is located at, you have to loop from that index till the very beginning. Okay, so I'm going in this manner, right? And not from the beginning to the very end. So I'm going to go from some index till the very beginning, so till 0th index. And I'm just going to write a subpart, so 3a, for every index, perform a shift down operation. Perform, okay, my bad, I should just write it as shift down operation. I think there's only one functionality here, so maybe I can just write it in this way: 3a, right? 3. For every index, perform a shift down operation. That's it. So after I do this, after I follow only these 3 steps, right? Only these 3 steps has to be followed to implement the build heap, right? Build heap functionality. After I've done this, my array will be represented perfectly in the form of a min. Okay, my array will be represented perfectly in the form of a min. Let's see if we are right or not. So maybe instead of visualizing this in the format of an array, I'll just draw it in the format of a tree here, and I'll explain it gradually. Okay, so 100, then we have 5, 45, right? So 100 children is 5 and 45. For 5, the children is 3 and 6. So 3 and 6. Okay. For 45, the children is what? 7 and 8. 7 and 8. Now you might be like, okay, how are you computing this, right? So just consider 45, right? 45. It is at index 2. Where will be the first child at? It will be at 2 into 2 plus 1. So that's 5. I'm just going to pick the 5, the element at the fifth number, 7. So this is the first child. Where will be the second child of 45? 2 into 2 plus 2. So that will be, I guess, 4 plus 2 is 6. So the second child will be 8, right? Sixth index 8. That's how I'm computing. Okay, great. So cool. 45's 7 and 8 is done. I guess I'll just start with 3. So for 3, the first child will be at 2 into 3 plus 1, which is 7. So I'll just have 9 here. Okay. Then the second child will be at 2 into 3 plus 2, which is, I guess, 8. So at the 8th index, it's 13. Okay, cool. I'll pick 6, right? So the first child of 6 will be at 2 into 4 plus 1, which is nothing but 4 into 2 is 8. 8 plus 1 is 9. So at the 9th index, it's 41. It's 41. Now, the second child of 6, suppose the second child of 6 is nothing but is going to be at 2 into 4. So that's the location, right? So 2 into 4 or 4 into 2 plus 2, which will be 10. Is 10 here? Is 10 existing here? No. So that will be an array index out of bound exception, right? So I won't go over that because I'm assuming you guys know that. Okay. So this is it. This is our actual tree as of now. This is what it looks like. Now I have to convert this tree into a min-heap tree, right? And then I have to convert this in the format of an array itself using this array, and no extra space also required. Okay. No extra space also required. You might be like, okay, I'll just store all the elements one by one, and then maybe I can just sort the array and take corresponding values, right? No, I'm not talking about that. The constraint here is that, okay, you have to solve this in a big O of one space, which means you have to utilize 0 or no auxiliary space. Okay, let's see what we can do. So as I mentioned, let's follow the algorithm. Let's not deviate from it. Consider the latest or the recent parent. Okay, consider the latest of the recent parent, which means that consider the recent parent, which means that, okay, so if I consider this last value, right, 41, the recent parent is basically the parent of the last index, the parent of the sort of like the value at the last index. Okay, so when I'm talking about 41, what is its index? Index is 9. So what is the parent position of this index? The parent will be located at index. So let me write it clearly. It's not clear enough. Yes, the parent will be located at idx minus 1 by 2. So 9 minus 1 by 2 is nothing but 8 by 2, which is nothing but 4. So I'll have to pick 4. So 4 is here. So I have to consider all the values. I have to consider all the values from this mark onwards. So I have to loop from 4 till the very beginning 0th index. This is what I was talking about. Once I have found the 4, so as of now in the above example, my index value is 4, right? My index value is 4. So I have to loop from 4 till 0. That's it. That's what it says. And for each and every index value, I have to perform shift down operation. Okay, I'll just write it again, so that's not an issue. So this is what my boundary is. I don't have to look for any values ahead of 4, right? So I have to consider the values behind 4. So 4, 3, 2, 1, 0, 5 values. Okay, let's see. So I can happily say that 4, which is nothing but containing the value 6, is my latest parent or the recent parent. Okay, let's see what we can do. Now I have to perform what? Shift down operation, right? So let's perform it. I'm at 6 as of now, right? I'm at 6 as of now. I'll just perform here and update the values in the array, so you are clear with it. Okay, so 6, consider its children. What are its children? 41. And is there any second child? Like suppose second child X? No, there is no second child. So the minimum value as of now, it's 41. Is 41 less than 6? No. So I won't do anything here. 6 has been processed. Let's move to 3. Now 4 has been processed. Let's move to 3. Excuse me. So I'm at 3 as of now. What is the value? 3. Okay, let's pick 3 in the diagrammatic representation here. Cool. Now I have picked 3. I'll consider its children value. What is children? 9 and 13. What is the minimum of 9 and 13? Minimum is 9. Now I have the minimum. Is this minimum value 9 less than 3? No, right? It's greater than 3. So I won't consider it. Okay, great. This 3 index has been also done. Let's move to the second index. See how I am moving from 4, then 3 to 1 and 0. I'm gradually moving from the current index IDX, which is 4, till the very beginning 0, right? That's what I mentioned in the algorithmic part as well. Great. Now I'm at where? Second index. What is the value? 45. Let's see. 45 this value. Okay, 45 this value. 45. Consider the minimum of 7 and 8, which is nothing but its children. What is the minimum of 7 and 8? It's 7. Again, is this minimum 7 less than 45? Yes, it is. So what I'll do is I'll swap 7 and 45. I'll swap 7 and 45. So this will look something like this. So my 7 comes up here and 45 comes up here. Well, will this swapping be up here itself? No, I'll also swap in the array. Okay, so 45 and where is 7? 7 is here. Okay, so my 45 will come up here and 7 will come up here. Look how good this is, right? How good this is. Okay, now that this has been done, what I'll do is I'll move to the next index, right? Which is nothing but 1 as of now. So pick 1. Okay, pick 1. I'll just stick to the same color. Pick 1. What is the value at 1? Okay, so it's 5. Okay, pick 5. 5. What is its children? 3 and 6. Pick the minimum value of 3 and 6. It's 3. Okay. Is the minimum value 3 less than 5? Yes, it is. So I'll just swap, right? I'll just swap. So 3 will come up here. 3 comes up here. 5 is here. Now I'll continue this process for maybe like 5, right? So 5. What is the minimum value as of now for 9 and 13? 9. Is the minimum value 9 less than 5? No. So I'll just move now. I'll move now. So as of now, I can see that, okay, 4, 3, 2, 1 indexes are done. I'm at the very last index, 0. Let's see. So at the 0th index, what is the number? 100, right? 100. The number is 100. Okay. So what I can do is I'll just pick 100. What is the minimum value of 100? 3 and 7, right? Or the children of 100, 3 and 7. What is the minimum value out of them? 3, right? Minimum value of 3 and 7 is 3. Is this minimum value 3 less than the current parent value 100? Yes. So I'll just swap here. I'll just swap. I guess I forgot to swap 3 and 5 here. So this should be 3 and 5, right? This should be 3 and this should be 5. Okay. So as of now, 3 is smaller than 100. So I'll swap. I'll just swap. So 3 comes up here and 100 comes up here. So again, in the array also, I'll just swap. I'll just swap. So 3 comes up here. 100 comes up here. Okay. Now I'll just follow 100 along. Okay. It's not like I'm leaving it because I have to rebalance the entire array, right? Perform shift down. So 100, consider 100 again. The children 5 and 6, smallest is 5. 5 smaller than 100? Yes. So I'll just swap here. 5 and 100 get swapped. So 100 comes up here and 5 comes up here. Even in the array, I'll have to swap. So 100 and 5 gets swapped. So it will look something like this. 5 comes up here and 100 comes up here. Cool. Now, should I stop here? No, I'll just continue. So 100, right? 100. What are his children? 9 and 13. Smallest of them, 9. 9 smaller than 100? Yes, I'll swap. I'll just swap 9 and 100. So 9 will come up here and 100 will gradually come up here. Good. Should I swap in the array? Definitely. So 109 gets swapped. 109 gets swapped. So 9 comes up here and 100 comes up here. Okay. Now consider 100 again. So is there any children to compare? No, I'm done with this. Now my min heap array has been done. This is my min heap array. Min heap array. I've converted the array which the interviewer gave me using the build if functionality and the shift down operation to the main heap array as mentioned. And I have required, what is the space complexity here? It's big of 1 itself, right? I have not required any auxiliary extra space. Okay, let's verify now that, okay, am I right or wrong? Okay, is 3 the root value, smallest among all the values here? Is it the smallest among all the values? Yes, it is, because I can see that there is no value greater than or smaller than 3 in the below structure or the below levels, right? Okay, is this property following for each and every parent value? Let's see. 3 smaller than 5 and 7, great. 5 smaller than 9 and 6, great. 7 smaller than 45 and 8, cool. 9 smaller than 113, great. 6 is smaller than 41. Great. That's it. And if I just consider the leaf values, then there's nothing to compare it with. So that is also great. So this has been converted to min heap. Min heap. So this is what I was talking about in the algorithmic part, that okay, consider the latest parent, the recent parent, and as soon as you find the index, in this case, our example, the index was 4. Just consider all the values from the 4th index till the 0th index. So consider 4, 3, 2, 1, and 0, all of those indexes. And on each and every index, perform what? Shift down operation. Shift down operation. See, once you know the algorithm, right? Once you know the written part of the algorithm, which I've mentioned here, for each and every one. So maybe if you consider anyone, right? So this was for, I guess, shift down, right? This is for shift down. This is for, I guess, shift up, right? So if you just memorize, if you just understand what this algorithm says, or the sort of like the paragraph says here, right? You'll be able to easily code out the solution. Okay, that's it. Let me check. I think I should wrap up the session or no. Let's see if there is any doubt. No, there is no doubts. Okay. Okay, great. There's no doubts as of now. Maybe I'll just begin with the coding part later on, maybe in the next session, or I can begin with the shift up and shift down operations. Let's see what we can do. So maybe I can just explain the coding part here. Okay, for maybe shift up. Okay, shift up. So shift up function, I'll write the code here in a second. Shift up function, what is it going to require in the parameters of the arguments? Let's see. So I know for a fact that in shift up, I'm adding the new value at the very end, and then I'm performing shift up from there itself. So I can have the current index here, idx, where my value is, and then I can have the array itself, which is heap. Okay. By the way, there's an interesting thing here that if you all don't know, in Python, there is something called a heap module. Okay, you can think that of as a module. So import heap, not heap, but heap q, I believe so. Okay, heap q. So basically, what's happening here is that it sort of supports operations like heap push. I'm not sure about this heap q as of now. I think it's heap or heap q. I think I have to take a look at that. So it supports operations as follows. So heap push is one operation it supports, where I just provide the value and the heap, okay, value to be pushed. It supports operation like heap pop. Well, these are the few operations I know. There are a lot of them. Heap pop, I'll just have to provide the heap. Great. So these are the few operations which as of now I know there are a lot of them. So heap q supports. And with this operation, you can happily implement what? Insert and remove operations. Insert and remove operations. Well, what is the insert operation here? Insert operation is this one, heap push, right? Pushing the value into the heap. Remove operation is nothing but heap pop. Okay. So just by knowing this in maybe comparative coding, or when you are trying to code out any solution on some online platforms, you can use this. Okay. You can use this. It's not like you have to implement it from scratch, but many a times in the interview, it might be said that, okay, so you know about min heap, right? You know about min heap, but can you implement it? Can you implement it from scratch? From scratch? That's the real question, right? It's not really hard as of now, because as of now, you know the things, right? So can you implement it from scratch? That's the question which many of the interviewers ask, right? They don't even go for max heap, because they know that, okay, if you can implement min heap, you can implement max heap as well. Okay. So that's it. So basically what I was talking about is that shift up is going to take some arguments here, which is nothing but current index and heap. Okay. Now that I have the arguments here, current index and heap, what was the real comparison operation going on in shift up? The comparison operation was going on that, okay, so for the current IDX, I'll compare it with the parent IDX. So is it not okay to compute the parent index here? Yes, it is. So what I can do is I can write here that I'll compute the parent index. Okay, I'll just so maybe just move to this part. Suppose an array is given. Okay, an array is given. Suppose the array is following the min heap property as well. Okay, min heap property. So maybe I can just take this array itself. It's not an issue. If I just take this 35796, so it's something like 35796. I'll just leave it as of now. Okay, 35796. Okay, this is the array given here. So let's represent this array, or let's call this array as a heap as of now. Okay, so this is a min heap as of now. Okay, this is nothing but a min heap. Okay, min heap. This is a min heap. What I can do is I'll have to perform what? I'll perform shift up operation. Okay, I'll perform shift up operation. Let's see what we can do. So to call shift up operation, we cannot call it directly. We have to call it using a helper function, which is nothing but insert here, right? So I'll also have to declare the insert function, or declare or define the insert function. Okay, so shift up operation slash function, insert function. What is it going to take? Let's see. Define insert. Okay, as of now I'm not writing the hardcore class representation. Just understand what's happening here. Once you understand, you will be able to do it quite easily. Okay, so insert maybe new value. I can write insert new value. This is my function name, insert new value. Okay, let's see what we can do. What is this going to take here? What is this going to take? It's going to take something like the value to be inserted and the heap, because see, there can be 10 or there can be 2 heaps or maybe 3 heaps in the program. So you have to specify which heap, right? So suppose I'm talking about heap 1, heap 2, and heap 3, right? 3 heaps. And I'm talking about insert a value 5, but I'm not mentioning the heap. So the program will get confused, right? Or even someone reading my code will get confused in which one of the heaps I'm trying to insert. So I have to provide what? Heap value as well. So therefore I've written heap. Okay. Now that this has been done, what I can do is I have to add the value to the very end. So I can just write heap dot append value. Heap dot append value. This is a really good sort of like thing here, right? That because I just mentioned what's happening. Excuse me. So I'm appending or inserting the new value at the very end of the heap. Okay, so I'm appending or inserting the new value at the very end of the heap. So this is what it takes care of, heap dot append value. Now I have to call the shift up operation. Okay, I have to call the shift up operation. So before that, maybe I can just define the shift up functionality here. Define shift up, as simple as that. Again, I've mentioned that it's going to take what? It's going to take 2 arguments here. I think I might have lost the track of it. It's going to take 2 arguments basically. Yeah, it got lost track of it. Cool. So it's going to take 2 arguments. It's current index, current IDX, and the heap data structure. Because again, I've mentioned you have to provide which heap you want to perform shift up operation on, right? There can be 100 heaps in the program. So I'm just going to write in pass. I'll complete it as of now. So heap dot append value. What should I do next? I'll just call what? I'll just call my shift up operation. So I can just simply write shift up. I'll have to write the current index as of now. So what is my current index? What is my current index? Well, it's the index where the value has been inserted. And what is that? It's nothing but length of heap minus 1. Okay, length of heap minus 1. Now I have to provide what? Secondly, I have to provide this heap here. So I can just have heap as well. This is it. This is how I am calling the shift up function here. So I can just write calling the shift up function. Okay, calling the shift up function. Cool. Now that this has been done, my program will take care of it. Let's implement the shift up as of now. So as of now, I know that in shift up, for a current index, I'm comparing it with the parent index. How's the comparison going? So if this current index value is smaller than the parent index value, so it's something like this, I'll just swap, right? So for that to happen, I have to compute the parent index as well, right? So I can just happily write that declare or declare parent index. You can even write this as compute the parent index. Okay, it's not a hard and fast rule that you have to follow what I'm doing. So declare the parent index. Okay, how will I name the parent index? Maybe PIDX or parent IDX. This looks completely fine to me. What is the formula for this? This is something which I have mentioned in the previous session. or the yesterday's session. So the formula is current index minus 1 by 2. You might be like, okay, why am I doing this, right? Why am I doing a double division? Well, this is nothing but a floor division in Python, right? Another way to implement this is something like this. So maybe you can import a math. Okay, you can import a math, and contradictorily, you can write something like this. So maybe I can just write it up here itself. Instead of this, you can write what? Math dot floor what? My current index. So suppose IDX it was by 2. So this can be a different implementation of that. But again, you have to import something, right? Which I believe so in the interview it's forbidden. In the interview it's forbidden. So you have to import math in order to do that. Okay, you have to, in order to do this math.floor index by 2, you have to import math. But I believe so you can talk with the interviewer. If he or she allows, it's good to go. Then if it's not allowed, then definitely don't use it, right? So parent index will be current index minus 1 by 2. So this is taking care of the floor division, which I've mentioned earlier. Now that this has been done, here's something which I have to take care of. What is it? Let's see. So suppose at some point of a time, this is my this is my tree here, B, C, and D, and E. Suppose I'm performing shift up operation from E. Suppose E gets swapped with B, so E comes up here, D comes up here. Now, suppose E gets swapped with A, so E comes up here and A comes up here. Now, should I compute the parent index of E now? Since E is at the very root. Now, the E is at the very root value. Is there nothing but the root value? Or in the array, it's at the 0th index. Should I compute the parent of it? Should I compute the parent of it? No, I should not. Why? Well, it will be array index out of bound exception, right? Well, in Python, it won't be really really a thing like that. Suppose I'm talking about 0. So 0 minus 1 by 2 is actually going to be the 0, right? Not an issue. But suppose it turns out to be something like minus 1 or minus 2. But in Python, minus 1 and minus 2 are valid or legit. How? Negative index in Python is supported. Negative index in Python is supported. Therefore, I'll just make use of the comparison operator. Okay. So when I'm gonna check that. Okay. So while my current index is greater than, equal to, or maybe greater than 0. Okay, greater than 0. Because when I'm writing greater than equal to 0, it's going to go in for a value which is equal to 0, right? That's not what I want. So while my current index is greater than 0, and what is the condition here in shift up? What is the condition? That my parent value is going to be what? So my current index value is going to be smaller than the parent value, which means my parent value is going to be greater than my current index value. So I can just write heap at the parent index. Parent index is what? It's actually greater than the heap value at where? The current index. The current index. So I believe so it should be current index. In that case, I can maybe declare a helper function, define swap. That will also make a lot of sense. And the swap functionality is going to take the first index. So maybe IDX1, it's going to take the index 2 and the data structure from which it's going to swap, right? And then I can happily swap here. So heap at IDX1, heap at IDX2 is going to be assigned in the following ways. So this should be IDX2 and this should be IDX1. Well, you can use a third variable. Sorry, you can use a third variable called temporary, right? Just to make sure that the swap functionality is happening. But this is the beauty of Python, right? You can just do it in one line. Okay. Now that this has been done, this is what the condition is checking for. That okay, so the current index is greater than 0, and the parent value in the heap is actually greater than the current index value. Then I can swap. Okay, my bad. Then I can swap the values. What? Just swap the current index. This is my first index which I'm passing, my parent index, and then I can pass the data structure which is heap. I can pass the data structure which is heap. Now that this has been done, it's swapped, right? It's swapped. What else can I do here? I have to assign my current index to the parent index. I have to assign the current index to the parent index, and my parent index will be updated as follows. So current index minus 1, and this will be again a floor division of 2. So by 2 will do fine. And this is it. This is it for the shift up operation. See, when I'm mentioning about the shift up, I wrote a lot of steps there. 1, 2, 3, 4, 5, 6 or 7 steps, right? But as of now, I can see that it's hardly 3 steps here, right? 3 or 4 steps in the algorithm, the coding part. So once you understand that, you will be able to easily implement this. Okay. So let's check if there is any doubts. Okay, I'll tell I'll tell one of the members to create the playlist. Not an issue, Neil. Also, how many sessions will be these? Will this be okay? Uh, Basically, I think this is nothing but the day 10, right? So I believe so. 10 community sessions have been done as of now. The first one can be thought of as a community session. This was an induction session. So 10 to 9 sessions have been done as of now. So there will be roughly more sessions. I cannot tell as of now because it's going to change according to what the syllabus is. So for example, if I'm talking about covering the dynamic programming playlist, tree graphs in depth, then it's going to be a lot of sessions, but we will see to that. It's not like it's a fixed session or fixed amount of time. So if you, I think the count is 9 as of now. So it looks like many people joined as of now. So what you can do is that go through this video to understand the mini heap functions or the operations, which are quite essential for the interview. If you find it useful, you can give it a like or something like that. And this is it. Also, today also I have explained about the coding part. As of now, you can see on the screen, it's shift up operation, right? This is the shift up operations. And then also I've explained about this, all of the functions, right? So insert, remove, which within each and every step. Also, I've explained about the build heap functionality for those who are new here as of now. So this is nothing but the build heap functionality, which I've mentioned here. Okay. So each and everything has been mentioned. So you can sort of watch the video again, or when the session gets over, you can watch that again. I believe so. I'll just cut the session off as of now. We'll meet in the next sessions. Okay. Thank you for tuning in. We'll meet in the next session with the coding part for shift down. We'll meet in the next session with coding part. I'll just write the agenda here. We'll meet in the next session with next session. I'll be talking about coding part of what? Shift down, which is nothing but also going to implement the remove functionality there, right? So shift down function, remove function, and the very important build heap. Well, build heap is going to have roughly 1 or 2 lines of code, and it's going to call shift down recursively or for each and every index. That's it. So this is it. We are going to discuss this in the next session, or maybe I can even talk about the shift up for those who are new. Okay. Thank you.